Welcome. We are now in the middle of module 2. We have seen in previous lectures the input output structure of the flow sheet and the factors that govern the decision of batch versus continuous process. In previous lecture, we tried to develop overall material balance for a process from the input output structure of the flow sheet. That means, without going into the details of the process, from outside the process we try to evaluate the flow of reactants, the flow of products, and we try to develop a material balance based on the selectivity of the process. And then we had developed stream table that now I will show from using HDA process as a case study. What you see on screen now is the input output structure of HDA process. The process with two feed streams, hydrogen, methane and toluene, and then the products are benzene, the main product, and the side product diphenyl. The hydrogen is fed in excess, therefore it comes out as unreacted gas, and then methane is an impurity in the process. It enters also with the fresh hydrogen feed stream, and it is also generated in the process as a side product. And to keep the methane concentration under limit in the process, we have to purge some of the unreacted gas. So, we have a purge stream and a recycle stream. So, this is input output structure of the flow sheet. Then we try to identify design variables. The design variables that we identified were the rate of production of benzene, the main product, then the mole fraction of hydrogen in the purge gas and the selectivity, and based on that we developed an overall material balance in which we tried to derive expressions for the fresh feed rate of toluene, then the fresh feed gas, then the purge gas in terms of all the design variables, that the production rate of benzene Pb, selectivity S, and YPH, which is the mole fraction of hydrogen in purge gas. Now, when we have only two reactions, as in case of HDA process, such kind of approach could be adopted. However, in many processes there are very large number of reactions, several main reactions, several side reactions, and therefore we have to develop generalized material balance in which we will use the conversion of each of the reaction as a variable. Now, let us try to see that approach for the material balance. Alternate approach for material balance. Now, here we will use the extent of a reaction as a parameter, or fractional extent of a reaction. And that we will denote by letter zeta. Okay. Now, let us try to develop material balance for the HDA process with this approach. Let us say that zeta 1 mole or mole per hour in case of continuous process of toluene react with zeta 1 mole or mole per hour of hydrogen to produce zeta 1 mole of benzene or mole per hour again in case of continuous process, and the second product is methane. This for the first reaction of the HDA process. In the second reaction, 2 zeta 2 mole or mole per hour of benzene react reversibly to produce zeta 2 mole of diphenyl and zeta 2 mole of hydrogen. So, when we do material balance, the net moles of benzene become zeta 1 produced in the main reaction minus 2 zeta 2 consumed in the side reaction. Methane is zeta 1 moles, diphenyl zeta 2, toluene consumed, which is the limiting reactant in the present situation, is zeta 1, and hydrogen consumed is zeta 1 in the first reaction and zeta 2 moles that are produced in the second reaction. Now, in case of multiple reactions with multiple products, we can write a generalized expression as moles of a particular component J are equal to N J naught, which are the initial moles, plus nu I j into zeta I. Now, I here indicates reaction and J as a component, which could be either reactant or product. Now, nu I j are what is known as reaction coefficients or stoichiometric coefficients. Nu I j values are positive for a reaction if a particular component is produced in the reaction. That nu I j are positive for a reaction I if a particular component J is produced in the reaction, and obviously Vij will be negative for a reaction I if a particular component J is consumed in the reaction or is the reactant in that reaction. Now, in such a approach, we can very easily create a matrix of calculation in which we will write all the stoichiometric coefficient in matrix form and then multiply it by the matrix of extent of reactions. Such a system can be very easily solved on a computer to get like material balance of all the components of the process. Okay. Now, let us try to develop the relation between the two approaches. Again, using the HDA case study as an example. Now, zeta 1, which was the moles of benzene produced, in the earlier approach we wrote as Pb by S. Okay. Similarly, the net this zeta 1 is the toluene consumed. Toluene consumed is Pb by S as per the first approach and zeta 1 as per the second approach. Then the rate of production of benzene Pb as per the second approach is zeta 1 minus 2 zeta 2, and therefore, by combining these two expressions we can write zeta 2 is equal to half zeta 1 minus Pb, which is equal to Pb by 2 into 1 minus S by S. So, essentially we have the two expressions, zeta 1 corresponds to Pb by S and zeta 2 corresponds to Pb by 2 into 1 minus S by S. Now, after evaluating all the molar flow rates of streams, we have to evaluate the economic potential of the process. Based on the input output structure that we have developed. The economic potential EP would be the cost of all the products plus cost of all the byproducts minus the cost of raw material, because these three components we have determined. Okay. This would be the general definition of economic potential at the input output structure of the flow sheet, that is level 2 of the design. Now, again for the HDA process as example, we can apply this general definition as economic potential is equal to product of the process is the benzene. So, cost of benzene. Now, the side product of the process is diphenyl, which we utilize as a fuel in the process. So, the fuel value of diphenyl the purge gas that comes out of the process comprises of hydrogen and methane, both are combustible gases. So, that purge gas can also be used as fuel in the process, captive consumption. Okay. So, fuel value of purge minus now the raw materials. Okay. The first raw material is toluene and the second raw material is hydrogen. With impurity of methane. Now, this is a very crude definition of economic potential. What it means is that we have a process that is existing and we do not pay anything for the utilities cost, which is of course is not possible, but this is what this economic potential means. So, that point we note the economic potential at level 2 of the design input output structure of flow sheet is the annual profit that we make if there are no capital cost and no utilities cost. Now, if the economic potential at this stage comes out to be negative, then the process is absolutely unprofitable. That means there is no point in designing the process further. Now, in such case, we have to look for alternate raw material or alternate process itself that has different chemistry. So, to summarize this particular level of design, what we have done is that we have identified the process variables, we have tried to derive an overall metal balance, and with that analysis we have developed the process alternatives. What are the process alternatives? With again HDA process as example. First is whether to purify the hydrogen feed stream. Second, whether to remove, recycle diphenyl, and third is whether to purify the hydrogen recycle stream. Now, obviously, with these process alternatives, we generate large number of flow sheets, and it is impractical to design all the flow sheets to a great detail. Therefore, we are trying to develop a criteria for screening of these alternatives, so that we can shortlist only the best few which we can design in detail. Having said this, we now go to the next level of design, level 3, which is the recycled structure of the flow sheet. We may know the product distribution as a function of conversion from the chemist. And if the desired products are formed at relatively low conversions, then we have the problem of very large amount of unreacted reactant left out at the reactor exit, which we have to separate from products and recycle back to the process. Now, separation and recycling becomes an important aspect of process design. Especially for gaseous reactants, we need a compressor, which is an expensive piece of equipment in terms of both capital and operating cost. As far as liquid recycle is concerned, we may need only a pump, which is not not at all an expensive component. However, separation of the liquid reactants from the other products could be an energy intensive operation. Now, this usually takes place through distillation columns or distillation train. Okay. So, now let us see what decisions that we need to take while deciding the recycle structure of the flow sheet. Of course, recycle structure of the flow sheet will also be dominated or will be influenced by the reactor design, because the conversion itself depends on the reactor design. So, that point we note, that reactor design governs the extent of reaction or the conversion and thus also influences the design of recycle structure. We also note the point of gas recycle needing compressor, which is an expensive piece of equipment. With high operating cost, and thus gas recycle is an important aspect of the overall recycle structure of the flow. Now, let us list the decisions that we need to make while deciding the recycle structure. The first decision that we need to make is how many reactor systems are required and should there be any separation between these systems. The next decision is that the number of recycle streams. How many recycle streams are required? We had dealt with such a decision before in case of input output structure, where we determined the number of product streams, and then we said that if the phase of the component and the destination of the component is same, then these components could be sent through the same stream. And the thumb rule that we used for such a decision was that it is never beneficial to separate and remix two streams. So, we shall see a similar analysis in case of number of recycle streams. Then third, should an excess of any reactant be used? Then the next decision is that whether a gas compressor is required. And then what should be its capacity and the typical cost. Another decision that is indirectly associated with the recycle structure of flow sheet is the mode of operation of the reactor. Whether the reactor be operated adiabatically or whether it should be operated isothermally. Now, this question will mainly occur for processes having a highly exothermic or highly endothermic heat of reaction. Then the next question that we have to answer is how to shift the equilibrium conversion if the reaction that is occurring in the process is reversible. And finally, we have to decide the economic potential, that is, how do the reactor cost with recycled streams or with recycled structure affect the economic potential. Now, let us deal with these decisions one by one and with certain examples. Now, the first decision, that is number of reactor systems. We have been taking the hydrodealkylation process as the case study so far, and we again go ahead with the same. Now, in case of HDA process, we have two reactions, okay, that is toluene reacting with hydrogen to give diphenyl, to give benzene and methane, and 2 moles of benzene reacting reversibly to give 1 mole of diphenyl and hydrogen. Now, both of these processes are vapor phase processes. Their temperature and pressures are same. I had mentioned in previous lecture the range of temperature for this process, that is 1150 to 1300 degrees Fahrenheit, and pressure of 500 psi. Now, obviously, since both reactions are at the same temperature, same pressure, only one reactor is sufficient. In addition, we also note that this is a non-catalytic reaction. Therefore, for the HDA process, the number of reactors is 1. Okay. However, this may not be the case for other processes. Now, we take example of acetic anhydride manufacture. The chemistry of the process is that acetone is decomposed in a species called ketene with liberation of methane. Now, ketene is an unstable species, it forms only at high temperature, okay, and it can rapidly undergo conversion to more stable compounds like carbon monoxide and ethylene. Okay. This particular reaction occurs at 700 degrees centigrade, 1 atmosphere. Okay. Acetone decomposing to ketene plus methane, and ketene may undergo further dissociation to give carbon monoxide and ethylene, and then acetic acid is added to ketene to yield acetic anhydride. This reaction occurs at 80 degrees centigrade, although the pressure is same. Now, in this case, we need more than one reactor. Why? Because the temperatures of the two steps of the process are significantly different. Okay. Therefore, we need 2 reactors. For this process. The reactors are often numbered. So, we say that R1 is the first reactor in which acetone undergoes decomposition, and R2 is the second reactor in which the decomposition product ketene reacts with acetic acid to yield acetic anhydride. Okay. Now, while designing a particular flow sheet, it is very useful to associate reaction step with reactor number that we just did, and secondly the feed streams with the reactor number. Now, acetone will be fed to the first reactor, acetic acid will be fed to the second reactor. Similarly, we can also associate the components in the recycle stream to the reactor number. Now, we have to decide the number of recycle streams. We use the same thumb rule as we used for deciding the number of product streams for this, that it is never beneficial to separate two components and remix them. Now, having said this, how do we decide the number of recycle streams? Again, we see the phase of that particular stream and then the destination of that stream, that particular component. Okay. The phase of the particular component can be found from its normal boiling point. And then the destination. And if the destination of the particular component or components, the different components is same and their phase is same, those components can be sent through the same stream. Okay. Now, let us try to apply this rule for the HDA process. What are the components of HDA process stream that comes out of the reactor? Hydrogen, methane, then unreacted toluene and the two products benzene and diphenyl. Okay. The destinations of these components are hydrogen and methane go to either recycle or purge. Toluene, unreacted toluene is recycled to reactor, but in liquid phase. Benzene is the primary product which is recovered and goes for further processing, and diphenyl is a side product which is used as fuel in the process, that is captive consumption. Now, the normal boiling points of these components are hydrogen minus 213, methane minus 161 degrees centigrade, benzene 80, toluene 110 or 110.8, so we can approximate at 111, and diphenyl 255. Now, obviously, hydrogen and methane can be sent together. Toluene forms a separate stream because it is in liquid phase and it is recycled to the reactor. Benzene is third stream and diphenyl is fourth stream. So, together we have two product streams, two recycle streams, and a single purge stream where methane and hydrogen are purged together. Now, let us try to apply the same for the acetic anhydride process that we saw. Here we have many components. Unreacted reactants, acetone, acetic acid, then the main product of the process, acetic anhydride, then the three side products with decomposition of acetone, carbon monoxide, methane and ethylene. Their destinations are the gaseous products, carbon monoxide, methane and ethylene are used as fuel. They are byproducts of the process and they undergo captive consumption as fuel. Acetone is recovered and recycled, however, to the first reactor, and acetic acid is also recovered and recycled, but to the second reactor, and acetic anhydride being the primary product is recovered and sent for further processing. Now, in this case there will be total 2 recycle streams, one product stream and one or you can even associate the fuel byproduct as a product stream. So, essentially 2 recycle streams and 2 product streams. Okay. So, this is how we determine the number of recycle streams of the process. Now, the question of excess reactant. Usually excess reactants are fed to force the conversion of limiting reactant to completion. In some cases, excess reactants are fed to suppress formation of side product. In some cases, excess reactants are fed to prevent coke formation, or they are also used as the heat diluents or heat carrier, which help in limiting the temperature rise of the process in case of highly exothermic reactions. Okay. So, now again let us see some examples for determination of excess reactants. Now, one example in this case is the production of isooctane, in which butene reacts with isobutane to yield isooctane, and butene undergoes a side reaction with isooctane to yield higher hydrocarbons like C12. Okay. Now, in this case butene is an unsaturated molecule, so it has high reactivity, and therefore isobutane is fed in excess. And this improves the selectivity towards isooctane formation. The larger the excess, the higher the selectivity. However, the stoichiometry is same. If we feed high excess of isobutane, we have high isobutane left unconverted at the reactor exit, and recovery and recycle of isobutane becomes a cost expensive component. Therefore, while deciding excess of a particular reactant, we have to determine the optimum excess. Now, take example of HDA, hydrodealkylation. In this case, hydrogen is fed in excess. Now, hydrogen has several roles, like it forces higher conversion of toluene, since hydrogen is also formed in the side reaction, reversible side reaction, excess of hydrogen shifts the equilibrium to left towards the benzene side. So, it suppresses diphenyl formation. Now, in some cases decomposition may occur, like if the temperature exceeds 1300 degrees Fahrenheit, then toluene may undergo decomposition and the coke that is formed may deposit on the reactor wall. Hydrogen helps in burning of that coke. So, the third role excess hydrogen plays is burning of coke deposited on the reactor wall due to thermal decomposition. And finally, excess hydrogen also helps in limiting the temperature of the process, because it acts as a heat diluent, it absorbs heat. Another example could be that of phosgene formation. Phosgene is also known as war gas. In phosgene, the carbon monoxide reacts with chlorine to give COCl2. Now, in this case, carbon monoxide is fed in excess to force chlorine conversion to completion. In some cases, the products may be very difficult to separate from reactants due to chemical similarity. A good example of this category is that of cyclohexane manufacture. Now, here hydrogenation of benzene is carried out through a reversible reaction. Now, cyclohexane and benzene are chemically similar and the relative volatility is very close to 1. So, if any benzene remains unconverted in cyclohexane, removal of it is very difficult. Secondly, benzene is carcinogenic. It is one of the hazardous or toxic materials. So, leaving impurity of benzene in cyclohexane is not desired. Therefore, excess of hydrogen is used to force conversion of benzene to completion. Okay. So, that point we note. Excess of hydrogen is used to force conversion of benzene to completion. We shall see a detailed analysis of this process later in this module. The bottom line is that due to this excess, the molar ratio of reactants is an important design variables. As we pointed out earlier in this lecture, the excess has an optimum. You have certain beneficial effects of using excess. However, there is always undesired consequence of recovery and recycle of reactant, and that needs to be considered while finding out the optimum excess. Unfortunately, there are no thumb rules for this. We have to determine the optimum excess for a particular process through iterations, okay, and that governs the recycle structure of the flow sheet. Heat effects of the process are also related to the equilibrium conversion. Okay. However, we shall deal with this topic in greater detail in the next lecture.